Okay, well, I'll make this very informal, so just interrupt me if you have any questions. We have a small group today. What I want to talk about is projects that are happening in Buzzards Bay related to mapping of salt marshes or monitoring of salt marshes. And what I have on the screen here is some work I did about 5 years ago, 6 years ago with the Buzzards Bay Coalition and an intern they had to map changes on a particular island in the Westport River. And you can see historical aerial images, and I've superimposed on that the 2013 boundaries so you can see what's going on. And I'll come back to that study a little bit.
Can I ask you a question?
Yes, go ahead.
The 38 and 44, those before the hurricane or after?
The 1938 was interesting. It was taken right 2 months after the hurricane of 38. It was in December. And it was one of the earliest post-hurricane assessments ever done by the federal government. And it covers most of southeastern Massachusetts.
And the
Parts of Cape
44
Cod.
hurricane.
The 44, I don't know what motivated that or the timing. I do have all the dates, but yeah, I think it was related to a hurricane as well.
Yeah.
A lot of the work by the Buzzards Bay NEP and the Buzzards Bay Coalition, our main partner on these studies, was initiated largely because of reports from residents about salt marsh loss and their concerns about it. So here's a site in the town of Bourne called Patchworth Marsh. It's a black and white, but it's in 1995. You can see there's some loss within those ditches, but it kind of looks fluffy and textured. So there's salt marsh grass there. Focus on the little X segment. 6 years later, this is what the site looked like. This is a summer photograph, so it's easy to see the marsh, and I've drawn an outline of the boundaries. And that X is that same little marsh segment. You can see the channels are greatly widening. There's loss all along the edges. And then the next photograph is 2021, and this is a color infrared. So in color infrared, anything with chlorophyll is red. So you can see quite clearly the dead salt marsh peat and the residual remaining salt marsh at that site. So there seemed to be a fairly rapid loss of salt marsh at the site. In my talk today, the purpose of this slide is just when I send you the PDF of it, it has links to all the various studies I'm going to reference. But one of the first studies that we got involved with, the coalition got some funding from the town of Westport to look at salt marsh losses in the Westport River. They noticed a lot of their islands were disappearing. These salt marsh islands were disappearing. And that was one of the first studies. I provided the GIS analysis and historical analysis and oversaw the intern doing that work. The coalition did a lot of sampling in the field. After that, we started the long-term salt marsh study about 2019, and this is ongoing and we'll continue doing it every single year. And this was started with Buzzards Bay NEP funding and some coalition funding to look at monitoring at 12 sites where we have established permanent transects and benchmarks to carefully track vegetation and elevations at those areas. The NEP is now funding a project with UMass Dartmouth, Dan McDonald and Civil Engineering, Environmental Engineering Department, and they're using unmanned aerial systems, drones, to map these salt marshes, these long-term study sites. And I'm going to show you some pictures of that. And they're also doing photogrammetry using drones, and I'll explain about
Joe,
that.
can I just, is 2019 the sort of the longest salt marsh study we have in this area?
That's when it started, right?
Yeah, I mean,
That's
are there other salt marsh studies that are been carried on, you know, prior to 2019 in the Buzzards Bay watershed? Or is this...
Absolutely. I'm just I'm
Okay.
just focusing on the ones that are doing historical
Yep.
changes that we're involved with. The real long-term historical study was in the Sippowisset Marsh.
Okay.
And there you have had scientists studying that marsh since the early 1970s.
Okay.
So yes, I'm mostly focusing on the broader range of work on Buzzards Bay that's been going on really in the last decade. And then in 2020, some partners that we were working with, scientists, got a grant from SNEP to study the use of runnels as a management tool. Runnels is kind of ditching. It's a shallow form of ditching used to drain pans in salt marshes, and I'll talk about that. And then building upon this long-term study site, another scientist, again, I'm listening to people here, led by Linda Deegan. She is doing this long-term evaluation of habitat and wildlife in these salt marsh areas. The previous study is being led by Alice Besterman, a postdoc with the Buzzards Bay Coalition. And then other studies I'm not really going to get into. There's a statewide CZM UMass Amherst study that's doing some statewide evaluations, but they have a site in Horseneck Beach. And there's a link to that. And there's a study that Westport River Watershed Alliance is doing with Rhode Island and Connecticut scientists to look at the loss at that site within the Westport River. So those are some ongoing studies, but the real granddaddy of all the salt marsh studies is the Woods Hole salt marsh site, a Sippowisset site. There's some work on in Bourne. I really don't even know who is doing that because those markers have been in that marsh for at least a decade. So I couldn't tell you about that, but there's a lot of work going on salt marshes. Just some really big basics. Salt marshes exist in the intertidal zone. And I will speak about specific tidal datums. A tidal datum is just a reference point. And so you're familiar with a lot of these, particularly if you're a conservation agent. The tidal datums are mean high water, mean low water, mean higher high water, mean lower low water, and local mean sea level. And these are averages of the predicted tides, not actual tides, of the predicted tides over a 19-year period. So we have semi-diurnal tides here, which means we have a higher high and a lower low and a higher low and so forth. So this is the characteristics of tides, and the tidal datum, mean low water, is your 0 point. And this is just, I only want to, just another site. Oops. Just to touch briefly on this, again, if you're a regulator, each one of these tidal datums means something. But for the purpose of this study, the only thing that's really important is, let me just close this down on my window, is that salt marshes are defined by the high tide line at the top and usually around local mean sea level or a little bit higher at the bottom. The high tide line is not mean high water, mean high water. It's the highest tide of the year. It's the king tide, as it's popularly known today. It's also very close to what NOAA publishes as the highest astronomical tide. So salt marshes exist in regulations by an elevation. And that's important to know. And you can't judge where the high tide line is because, well, here's a king tide. I took this photograph during a king tide and it created a rack line. And you see a rack line above the highest tide of the year, and that's a storm tide rack line. So there's different rack lines, and you can't use those rack lines to judge where these jurisdictional boundaries are. To see this a little more clearly, salt marshes, again, exist between the high tide line here in this graph. It's a little bit over 3 feet. And then it goes down to close to local mean sea level, or sometimes a little bit above it. So this is an example is for Round Hill, Dartmouth. And I have a picture there of the high tide bush, which exists near the high tide lines. The high tide bush is either frutescens, and we use that in our monitoring studies. So here's what the marsh looks like in the wintertime. But you can see the low marsh is Spartina alterniflora out there. Then you see this lighter colored grass, the salt marsh hay, Spartina patens. It's mixed with Disticulus and Juncus. And then you have the high tide bush, which is this entire area is inundated during king tides. Different marsh species. Now, I just defined salt marshes as existing between specific tidal elevations. Well, you probably realize that tidal range varies dramatically in Massachusetts. In Cape Cod Bay, the tidal range is 10 feet, whereas in Buzzards Bay, it's only 3 to 4 feet. So as you can imagine, tidal marshes on the North Shore and in Cape Cod Bay occupy a much larger elevation range than in Buzzards Bay. And you're familiar with, if you're a boater, that some parts of the Cape, the tides are on Boston tide schedule. Buzzards Bay is on Newport. And then in between, because they're offset by 3 hours, they cancel each other out. So if you've ever walked along the bike path in Woods Hole, the tidal range there is only 1 foot, believe it or not. You go there and even on high tide and low tide, it almost looks always the same. So given that situation, if I have 1 foot of sea level rise in a certain amount of time, which marshes are going to be most affected? That one. Obviously, the areas with the lowest tidal range.
Yeah.
So in Buzzards Bay, the area with the lowest tidal range is Dartmouth and Westport. And then as you go further up in Buzzards Bay, toward Bourne and Wareham, it gets closer to 4 feet, and it's closer to 3 feet down there. And of course, if you're on the south side of Falmouth, that has almost no tidal range. So this is the actual tidal range, elevation range that marshes exist around Massachusetts. Again, the smaller the tidal range, the greater the vulnerability to sea level rise. And I just want to make a point, because I'm going to be talking about sea level rise. These tidal datums and these tidal ranges will not change with sea level rise. So sea level rise will run sometime in the future. It will be 3 feet greater than it is today, where mean sea level is, but we'll still have a 3 foot tidal range around Dartmouth and Westport and a 4 foot tidal range around Wareham. The tidal range is just defined by the mass of the moon, the mass of the earth in this body of water, and it's 6 foot, 6.5 feet in the central Atlantic, a bulge. And you see these different elevations because you have these water masses piling up or hitting each other. But in general, you can have 10s and 20 feet of sea level rise. You're still going to have the same tidal range. It's just that the coastline is just going to be changing
Significantly.
So here are the long-term study sites around Buzzards Bay. You can see a couple in Falmouth, a couple in Bourne, Wareham, Marion, and so forth. In terms of the long-term study, what the Buzzards Bay NEP role is, and it's mostly on me because I'm the one at the NEP who's mostly doing this work. It's the historical mapping of boundaries of the. I'm doing the GIS work to map those boundaries. I'm analyzing LiDAR data. The NEP, with support from Mass Maritime students, installed benchmarks at all the sites. We're conducting elevation surveys, and we're training the coalition staff to do elevation surveys, and we're evaluating surrounding land use. So the Buzzards Bay Coalition role is more vegetation mapping, species abundance, crab population monitoring, the integrity of the peat and other biological things. And then we have scientists coming in at these sites with grants that they get to do various experiments and evaluations. So this is what the goal of this program was, is to establish these sites, have this great information and permanent transects that people can come and look at and have good elevation data that they can use, and then continue to have those scientists secure funding to study these sites.
So Buzzards Bay National Estuary Program, the purpose wasn't really for you to continue these studies. It's to allow other agencies and other NGOs to sort of continue the work by establishing these benchmarks?
That was my question.
The scientists are doing their own projects. Right now, the coalition and the Buzzards Bay NEP are committed to doing their pieces. So I guess as long as, until I retire, the NEP will continue to do all these analyses and the coalition will continue to do that. I mean, someone will replace my role eventually, but right now we're putting all these pieces together. We're documenting the methodology and it will be done in the future. The goal is to monitor these sites decades in the future. When we went to the towns to get our permits to do this project, we had to get a permit to install the benchmark and put markers in there. We told the towns that we'll be doing it hopefully for many years to come. Again, here's just a slide from the coalition of the kind of things that they do. They have transects. They put people out in the field. They look at these specific areas along that transect. And when you look at that guy over there measuring something, the canopy height in that transect, we have this rule that you can only walk on the left side of the transect line. You can never walk on the right side because that's the monitoring side. The other side is the your travel side. So let's take a big picture thing here. What affects salt marshes, where they are, and their distribution? Okay, if you think in geologic times, in geologic time and historical time, the primary driver affecting salt marshes is sea level rise. Unquestionably, for millions of years, we've been going through ice ages, warm periods, ice ages, and warm periods. Since the last ice age, about 22,000 years ago, once upon a time, Georges Bank was land. You had mastodons on there, or woolly mammoth, and you had a coastline there. Maybe you had some salt marsh, but as the ice caps melted and the coastline migrated, coastal habitat migrated with it. So 10,000 years ago, Buzzards Bay probably looked something like that. You had a forest in Nantucket Sound. Even as late as like 3,000 years ago, you could probably still walk from Pocasset to Marion along the shoreline. That was still the shoreline of Buzzards Bay. And you can see by the sea level rise that when the ice was melting, sea level rise was really fast, but then it slowed down as all these glaciers mostly melted. But it has still been rising. So since the last ice age, it's risen 400 feet around New England. Okay, that's the geological picture. But in terms of our lifetime and what we experience, the story is a little bit different. So sea level rise is still the primary driver. And when you look at the sea level rise for, that's the actual sea level records for Newport, it's risen about 1 foot in the last 100 years. And if you really look carefully at that trend, it's kind of flat during the 60s and 70s going to the 80s, and it's kind of going a little faster in more recent years. So that's the trend about rising sea level that they're talking about. But again, when you're talking about, when people are seeing things during their lifetime, there's other factors going on, and development of structures like seawalls and roads impede marsh migration and restrict tidal flow, and those are still having impacts. There are still lots of culverts going to salt marshes. Those culverts get blocked with sand and so forth, and you can sometimes have dramatic changes to marshes over a very short period. Coastal habitat is also affected by changes like the frequency of intensity of storms, changes in precipitation, summer and winter water temperature may affect the abundance of certain species, native invasive plants, what you see in the marsh. We have an issue with purple marsh crab suddenly causing a lot of grazing damage. And that may be related to species that prey on it. And then warmer water temperatures may affect the decomposition rates of salt marsh peat, and nutrient pollution may enhance marsh peat decomposition. making it less resilient to disturbance. You know, salt marshes exist on a pile of decomposing material. And if you ever tried to compost leaves in your backyard, you probably know that if you throw some fertilizer on that leaves and make the pile bigger so that it retains some heat, it'll decompose those leaves faster. So the same principle is probably happening in salt marshes when we have more nutrients coming from septic systems in the groundwater and it's seeping in that peat. It probably is speeding the decomposition, and you see peat collapsing in some marshes. So the patterns of marsh loss that you see around Buzzards Bay generally form these three patterns. In the image of Dartmouth, you see bare patches may appear inside the marsh. In internal marsh loss, you have these pans forming. Sometimes they can grow very big where all the grass dies off. And that's primarily from standing water. Then you see some pictures like this picture of Mattapoisett, and that may be an example of possible crab grazing. That's a winter photograph, I'll show you it. And then that Westport River image, that is undercutting of the bank by a channel, and that happens a lot on island marshes. So these are some patterns that you see of marsh loss around Buzzards Bay. And there is more of a summer picture in the purple marsh crab that may be contributing to that funny fringe that you see around marshes. And this has been well documented at a number of sites on Cape Cod, and they have linked it to the marsh grass. Normally you'd have tall spartina already growing in that fringe, but the crabs are nipping away at it.
Joe, can I interrupt real quick? Sorry, what was the photo from Dartmouth on the last slide? What was that, the cause there?
That was from standing water in the higher marsh area. That kind of situation can happen when a storm may bring in a lot of water into a marsh and the water has no place to go and it just sits there. And if it doesn't drain out, the plants get waterlogged and then they'll die off. So it's pan formation, and it will grow and expand potentially with that standing water.
That's
Thank you.
That's stormwater without enough flushing?
No, it's ocean water.
Ocean water.
So for example, I'm going to show you some pictures of Allen's Pond in Dartmouth, which is an interesting case because Allen's Pond in Dartmouth, the opening to the pond, the salt pond, periodically closes. And during one event, during 2014, there must have been a big storm. The channel, the entrance was closed, and a lot of water piled up and didn't drain from the marsh. And then we saw a big die off in the upper and central part of that salt marsh. So that is the mechanism of pan formation. It's natural, but it can lead to a lot of pans and pools in certain kinds of marshes. And I'm going to show you some pictures of marshes. They look pockmarked and they look very different than other kinds of marshes. But those form when water can't leave an area and then the vegetation dies, and then fish and other things can scoop out the sediments, and then you start having a deeper and deeper pool, a bigger and bigger pool growing.
Joe, this is Mark from Dartmouth. I would also suggest that when water, ocean water, gets confined and sits and can't drain, there's an evaporation that takes place while it's standing there, and salinities actually rise because the concentration of salt increases with the reduced volume of water. And plants we're talking about are, they have a specific estuarine salinity, which they exist in. And when we go hypersaline in some of these ponds, they can't tolerate it and they die off. It's a salinity problem too.
Yeah, thank you for pointing that out, Mark. And I'm definitely oversimplifying the mechanism of pan formation. But yes, if you have that water piling up during a summer storm and it's hot and it's dry and it's evaporating, it does get hypersaline, and that is contributing to the death of plants in that area. My piece of it is mapping salt marshes. I use aerial photographs, but I also, because, for my graduate work, I mapped the eelgrass, and I was diving all the time in Buzzards Bay and on Cape Cod. And I learned to recognize what I saw in an aerial photograph and what that was. Oh, that's a rock field. This is drift algae. This is eelgrass. I had to kind of relearn the same process with salt marshes because I stayed away from salt marshes. My advisor did salt marshes and I wanted nothing to do with salt marshes at the time. So I've had to teach myself, what I'm seeing when I'm looking at aerial photographs. So this is what it looks like in the field versus what it looks like in an aerial photograph. And I've been getting some oblique drone imagery, which I really hate, but it's better than, because you always want to have vertical aerial photography, but it is still helpful in helping interpret. So I'm just showing that same area from a drone. The other one was a picture from a boat and from a drone taken with an oblique angle. When you're mapping aerial imagery, you have a lot of things to deal with. The drone imagery I got from Westport was not orthorectified. They didn't have the sophisticated software. I had to manually do it and register all these points to match up with points on a real ortho photograph. Then I'm dealing with, in this example, 2001, a much poorer image quality than in 2021. So if you're doing photo interpretation, there's a skill and experience, and it can be very laborious to interpret these, but it can be done, and you can map what you think is a regional approximation. And if you get enough, a long enough historical record, the mistakes you make in 1 year, it eventually cancel out, so you can pull together what is, you think, a reasonable story. And again, this goes to just showing what am I seeing in the aerial photograph versus what's in the field. And again, that on the right, that fluffy texture is the tall Spartina. That was a November photograph. The other one's a June photograph. So there are bare areas. There's tall Spartina. There's the short Spartina. And again, you have to kind of understand what you're looking at. To do my mapping, I don't digitize every little inch of coastline. I create this library of contours that I generate from LiDAR data, and then I pick a contour line that best matches what I think is the salt marsh and the high tide line. I'll look at I have a website that tells me the high tide line for every part of Buzzards Bay. It's online. I should have put a link to it. DEP encourages Concoms to use it. It's in NAV D88. All Concoms and planning boards should be accepting that plans in that elevation datum. And you shouldn't rely necessarily, you should review where the high tide line is placed on plans for project near the ocean based on published high tide line information. So I rely heavily for setting the upper boundary by LiDAR, but then I photo interpret carefully what's going on. I ignore the upper boundary. It is too hard to map changes in the shoreline, in the dividing line between a marsh and the upland. So for my analysis, I keep that as a constant, but I know marshes are migrating, but I can't map it consistently enough. It's easy to map the outer edge of a salt marsh. It's easy to see where the water is and the marsh begins. You cannot tell what vegetation you're looking at the high marsh. So my maps and my documentation of marsh loss is the loss of the leading edge, the lower edge. I'm not offsetting it by what it is gaining. Now, in many areas, it's not gaining very much. People have seawalls, there's other features, roads that are blocking marsh migration, but it is migrating in some areas. So I just want to point that out. And you can see all kind of cool things in aerial photographs. I just have this example here of a trunk of marsh breaking off what it looks like in the field. And you can see these in the aerial photograph. And in 2012, I had one chunk of marsh breaking off. And then in the 2015, 3 years later, I had new pieces breaking off at the top. So this is a really neat way that you can document some of the causes of a marsh loss. Here's an example from one of the Westport Islands. That red line is the boundary from a 1934 topo map that was drawn from a 1934 aerial. Then I'm showing a 1954. Notice by that little arrow in the middle, this is fine straight channel. Somebody dug a fine straight channel right through that island. And I think, there's some homes with a dock over here to the right. And to get around that island, you have to go around the long sands. I think someone actually dug a channel, but you look at that in 1954, and then you look at the image in 2013, how that channel just kept on growing and blew through and grew into a big hole. And then you have other damage through thinner areas. But that undercutting of the channels that you see along the edges of the marsh, cut away the marsh, and then small pans grow into big pans, and everything gets bigger and bigger. So any edge of a marsh is a process of losing it. So the more pans you have, the more ditches you have, the more anything you have that creates an edge causes more rapid loss of the salt marsh over time.
How do you deal with sort of tide discrepancy in your aerial photos? Or just in your evaluations? It seems like, when you're looking at one photo versus other, sometimes due to tides, it can make a big.
Absolutely true. And that caused me a nightmare this summer because I was interpreting the 2019 in a certain way. And then the 2021 aerials came out. And I said, oh my goodness, I made a complete mistake on how I interpreted the 2019. I had to actually look up the time and the day. It was taken during a spring high tide with poor water transparency, and I wasn't seeing the bottom edge. And what I was interpreting as the edge of the marsh was really what I could see in that cloudy water. And then I had to crank up the resolution. So my answer to that is my image analysis is generally good, but it's bounded by the most recent and the last. So the most recent is probably the most uncertain, and until I get another one after it. So what I end up doing is I don't treat each one in a vacuum. I look at what happened in the next year and what happened in the previous year, and what am I really looking at? What's the tide? And that is the very difficult, laborious part of it. It's subjective. I'm making an interpretation. Marshes generally don't recreate themselves. So if I see something missing in the future, I know it's missing. If it's a good quality photograph. If there's gray areas in between.
Well, even the quality of the photographs. I mean, just over the past 10 years, the quality of the satellite imagery has gotten so much better. Has that caused you to have any sort of aha moments?
Well, my big aha moment was on my misinterpretation of the 2019. And I thought I just showed. Yeah, I mean, again, this 2001 versus 2021, that's an excellent example. The 2021, I can actually see where the water line is. So you can see the foam on the 2021, where the little waves are creating that little bit of foam. In 2001, I think the water level is actually above the low marsh, but you can't resolve it there. So what I end up doing is I try to look for a summer image, companion for every image I'm looking at. So we analyzed 4 dates, but I actually have 10 different dates that I've evaluated. And I'm looking at intermediate ones and summer ones, and I'm using that to interpret. So I'm constantly going back and forth. So if you do ArcGIS, you can turn off one image and look at another and keep on flipping it and saying, okay, it was probably this in this year and this in this year, and I'm gonna make my best interpretation. That's how it works. Very tedious, very laborious. I think I do a good job in general. I'm gonna show you some pictures.
Do you have any sites where you're taking your own photos, let's say going to a certain site, getting a drone up there and taking your own images so you can maybe get better resolution for that particular site?
That is exactly why we started this project with UMass Dartmouth, because the drone imagery is so good. And some of the imagery, unless I go out there, I'm really confused as to what I'm looking at, what vegetation I'm looking at. So we have the UMass Dartmouth team looking at all these sites that are going to be doing a early spring before the growth and a late summer, early fall before the freeze and frost die off. And we're going to continue doing that for the next few years so that we have a better understanding what I'm looking at in the aerial photographs. And hopefully that will go on in the future. But going back to 1950s, and I'm using fewer pixels. When I was a graduate student, I ordered all these images from NOAA. I still have them, and I rescan them and digitize them at the highest possible resolution because I was using them for eelgrass, and now I'm using them for salt marsh. So I have some of that imagery, and some of the pictures that you see here are from that. So here's how it looked in the Westport Islands. You can see for Bailey's Island, what is that, 15, 17 different dates that I'm looking at. So each one of those colors represents a different date, going from 1934 to 2016 in that study. And so the green is the earliest, and then it climbs up to the current. And you can see, what these different islands look like and how they had marsh losses. In that marsh in the middle, you can see that somewhere in the maybe 1960s or after that, some pans started forming in the middle, and you had a die-off in the center of the marsh. For whatever reason, it began there. So when we looked at what happened in the marshes in Westport, the Westport Island marshes, we noticed that the rate of loss seemed to be slower during the 40s, 50s, and 60s, and then started accelerating. And then in the last decade, it seemed to be getting faster. And if you look at just like the Bailey flat data, if I were to extrapolate a trend, and again, this is 100 years since 1938, the trend, if I had just looked at the data through the 70s, was that by 2084, 100 years later, I would still have about 40% of the area of the marsh island. But then if I extrapolate the trend from maybe the 80s and 90s, I would estimate that by 2038 or 2045 I have on there, I would only have around 20% of that marsh area. And then if I look at the most recent decade, I would probably only have 10%. So you can see that the rate is accelerating of loss. And I showed you what the sea level was, and the sea level has been relatively constant. It's been going a little faster in recent decades. So the question is, what's going on here? Is it just that slightly bit of extra sea level rise, or are there other things going on? Is it the frequency of storms, the timing of storms? Is it water temperatures? There's a whole bunch of
The first thing that jumped to my mind was boat wake. How much more boating is there than there was, back in the 40s and 50s, and that if you're losing these marshes due to calving and things like that,
Sure. That's another potential. Some of these marshes are not on the main channel. They're a little bit more protected, but and they still exhibit losses. But that's another factor. We didn't even talk about boat wakes. And we did talk about the channel. If the channel moved right against the island, it just like undercuts it fast. So this long-term study back in 2019 and 2020, I worked with some Maritime Academy students, and we installed benchmarks all around Buzzards Bay at these 12 sites. We did driving these rods with a pile driver into the ground. The one in Wareham went down about 50 feet. It's a steel rod. It's in this concrete casing, and it's covered with a lid. And you open that lid, and you see a little steel rod, and that's what you measure elevation from. You always need a benchmark to measure changes in elevation. You need a valid reference point. At a couple of sites, I put a brass marker in a large, massive stone. We then need to know the elevation of those benchmarks. We use this great GPS unit that Kevin recommended, Juniper Geo GPS with super duper software. We do it mostly now on monopods, like the picture on the right. And here's an example of the data, and it's probably too small to see here. But basically at Herring Brook, the 2 points that were valid, the other one was a float, we didn't get a good fix. But the 2 points in 2019, versus 2020, the position of that GPS unit was within 2 centimeters from one year to the next. And the elevation was within 2.5 centimeters, in other words, an inch, from one year to next. So if I keep on getting measurements and can't get in the average, I'm going to get a very good sense of what the real elevation is of that benchmark. And then you map and monitor elevations in the marsh from that. This is Mattapoisett Neck. And again, the points are very close to one another, and the elevations in this case are even closer to one another. Again, they're all within 2 centimeters of each other, and those are 3 different years of data. So again, we have all these transects established in marshes. We have all these monitoring devices set out there. We monitor tidal elevation. They have wells installed. And this is what it looks like at Ocean View Farm in Allen's Pond. And then the team at the coalition, they go out, they run tape measures between the markers, and then make observations. The other wonderful tool that we use is a Leica Sprinter with a barcode staff. It is super easy. I train these students each year, and they have no surveying experience. All you do is hold up the staff. It's a barcode, literally a barcode. And as long as that unit that you're looking through is perfectly level, there's bubbles on it, it records to a precision of 0.1 millimeter. And the repeatability is actually just a few millimeters. And so here's the staff. That's just, I'm not holding it correctly there. That guy is doing it incorrectly, but
it looks good though.
Perfectly straight. You don't cover up the bar, and he's just getting set up there. Well, I'm showing what the results are. So you go to the benchmark. They go 80 meters down the transect, getting measurements, and then they go back to the benchmark like 20 minutes later. So what's your starting mark versus your ending mark? So in 2019, with one team of students, they were within 1/10 of a millimeter, just putting the staff there and reading it through this instrument. And this instrument is maybe about 60 feet from that position. The next year, it was the same, a different group of students. And again, I'm getting these data sheets. I'm like almost not believing the repeatability. They're walking down the transect and coming back, and they're going back to the benchmark to get another meet, because you want to make sure they didn't bump the instrument, they didn't disturb it, and they're getting such repeatability. And then here's a plot of different, even with this very uneven bottom, you're putting this staff as you're going down the tape measure on this bumpy surface, maybe the shells, rocks, holes, and so forth. You can see in 2019, 2020, and 22, the surveys show tremendous repeatability along these transects. So it's a wonderful, wonderful, amazing instrument. And then you put it all together, and then you can perfectly document what the vegetation is, what the elevation is. You can match photographs to what you see in the aerial photographs. This is actually from a drone image. And then there I show what the pan looks like in the aerial photograph, and the pan looks like in real life. And there is how the tape measure is run from one pipe to the other. The other pipe on the side is actually a well, I think, a reference well. So we can document all kind of cool things. I'll show you a couple of cool slides. In Bourne, on one side of the road, there is a construction, a culvert. On one side of the culvert, on the tidal restriction side of the culvert, marshes tend to be perched, and they have a narrower range of growth. And then on the other side of the culvert, the marshes at a lower elevation. Here is a site where I matched up what the students are seeing in their vegetation transect to the aerial image. And where that arrow is, you can't see the words, but it says grass plus disticulus. And then to the right, it says disticulus. So when you look at that aerial photograph, you see this kind of like light tan area. That's a particular species of grass. And it's at that very specific point that the disticulous boundary ends. And I was able to perfectly match their observations to the 2018 image. Now, what happens if I look back into time, superimposing the same transect? Here is the 2005 photograph. You can see disticulus, which is a higher intertidal species, existed closer to the ocean. That patch of tan is larger. It covers more area. Let me go back. You can see that tan area is only near that arrowhead. And then you go back to 2005, that tan area, which is your disticulus then, was much more massive. So we're spending a lot of time mapping what's happening at the edges, but the marsh isn't changing really fast over that 20-year period, but the species on the marsh are changing rapidly. So I'm going from high marsh species, and they're retreating from the ocean across, in a very short time span. So that's an interesting thing that we saw. Another fun slide, when we set up the Allen's Pond project and the sites and the monitoring wells, we didn't realize that Allen's Pond had closed. That channel migrates back and forth, and sometimes it closes, and the town has a permit to open it up whenever that pond closes. So in 2020, Alice had set up this monitoring well, and she puts her little hobo monitoring unit. And you can see that in 2020, the orange is the tidal fluctuation compared to Newport. And you can see, again, a tidally restricted marsh. The elevation of the tide is perched, and it's a much narrower range. So that's that orange line compared to the blue Newport line. Well, they opened the channel over the winter, and then the next summer, when she started looking at the data, we were completely blown away. The wells were now going dry because they were too high to monitor low tide in Allen's Pond, and it was almost matching Newport. So there was almost no tidal restriction. It matched the Buzzards Bay tide, and we missed the whole lower tidal thing. But basically, you can see you went from a tidally restricted marsh to a well-flushed marsh. And Allen's Pond has done this many times. And one time that it did, it was in 2014. And you had these large areas in Allen's Pond, the marshes there, that died off during that tidal restriction. Maybe there was a storm that coincided with this restriction, but a lot of water got piled up and stayed in that pond, and big chunks of marsh died. So you can see in the summer 2014 on the left is this large area with no vegetation, but then you go to 2021, which is on the right, and the unvegetated pans are now quite a bit smaller, and there's now tall spartina growing around them. So some pans can recover naturally like this, but this is kind of an unusual situation because the pond opens and closes. The usual pattern is pans keep on growing bigger and deeper and getting deeper, and they don't recover unless the water can get out. And then finally, we're using remotely censored elevation, LiDAR data available from lots of sources. You know what LiDAR data is. You can now do photogrammetry with drones. In the olden days, that picture on the left was a guy making a topographic map. The old topographic maps, they had stereo images. You drew lines. You could actually measure the height of mountains with the stereo images. Well, nowadays, you can do photogrammetry with software using drone images that overlap. And it's very sophisticated, and you can do modeling, and that's what the UMass Dartmouth group is doing for us. So here's some LiDAR data showing some island marshes in Falmouth. And if you look at the loss of the marshes, unsurprisingly, most of the losses are the low edges of the marsh. So in this photograph, anything that is red was lost between 2014 and 2019, and it's generally the low marsh that is lost, unsurprisingly.
But it's interesting because when you showed that other one with the testiculus, that indicates that, it's just, that was kind of an eye opener for me with the, showing the vegetation even further back and how much that's changing. It's moving fast.
This slide here?
Yeah, no, the one where you had the vegetation overlaid between 2000 and I think it was 2008 and 2021, where you had the transect, the vegetation transect.
Testiculus, yeah.
Yeah.
So again, common sense, low marsh disappears more likely than high marsh. But you can have pan swamp. Now, here's what the UMass Dartmouth products look like. This is a site in Fairhaven, Little Bay North. This is 1.2 centimeter pixel sizes. Okay, I'm dealing with maybe 15 centimeter at best, commercially available NOAA sites, 1.2 centimeters. And I can create digital elevation models from that data. And here, you can see that the photo wasn't perfectly registered, but I can actually see the pipe that represents, the transect pipe. The image is a little bit shifted, but that black dot, that brown black dot is actually the pipe picked up with the photogrammetry elevation model. And those four things there are four rocks. You can create 1 centimeter contours. Just for fun, I took a very small area and I made 1 millimeter contours, which is absurd, but that's the ability of the software, how far you can go. So if you can if you have very small pixels from your drone, you can do 1 centimeter contours. And that is actually meaningful for our study because when you start talking about the runnels, they're very shallow. They're only like 4 or 5, maybe 10 centimeters deep in some cases. So if we look at what's happening in marshes, the marsh on the left is Allen's Pond, and they're color-coded by the mean elevation of the marsh. And the other site is Wings Neck and Bourne. And you see that there's a lot of loss in that northeast corner. In the Allen's Pond site, those marshes that are islands or lowest elevation, exposed near the mouth of an estuary or channel, those are the marshes that are most vulnerable. The highly ditched ones, the ones with a high percentage of pans and pools, or near high nutrient additions. I think the losses on this Wings Neck site in the northeast corner, it's hard to see, but there's ocean on the other side on the top of that Bourne site. But over on this side, there's a lot of houses and the groundwater from the mainland is coming into that site. So I think that might be a nutrient-related contribution that is exacerbating whatever is going on with sea level rise.
There's some historic alteration in that area as well.
Is there?
Yeah, that right corner.
But if you look at that, the green is 2001, the yellow is 2009, then it's 2014, and the red is 2019. That's what those different colors mean. So there is some rapid loss on the edges of those marshes just in that 20-year, 18-year period. So back to the Allen's Pond site, those little islands near the channels that are shaded purple, those are the first marshes that'll be completely disappearing there.
One of the really interesting things about this Wings Neck is you're actually starting to see all the historic lawns convert to salt marsh. So if you were on the north side there, all their lawns are people are really upset about it, but all their lawns are converting to salt marsh, and you can see it over the past 20 years. You can even see it in the 5 years I was there, that it's really, because that's a historic fill all along there. So it's sinking a little bit, and that whole area is the lawns are converting to marsh.
Did you tell the owners they couldn't mow it anymore?
We've had quite a few conversations.
Yeah, we're still dealing with that, definitely. No mowing. So Sam, you think, in my head, I was always thinking it was salt marsh that they mowed starting 20 years ago, but you're saying because it was fill, they probably set it up as lawn, and now with salt marsh migration, the lawns are becoming swampier and turning into marsh? Is that what you're thinking?
It's a combination of a number of things in there, but yeah,
Mhm.
the whole area is built on historic peat, so it's
Right.
sinking.
Mhm.
And then that's why we get that flooding along that road too. We've had a lot of issues with flooding because that spongy marsh is just, as sea level rises, there's no way for the water to go.
Mhm.
So the lawns are converting to marsh, and there's terrible problems with flooding on that, stormwater flooding on that road because there's nowhere for it to go anymore.
Right, right. Okay, interesting.
And as sea level rises, groundwater level also rises. So if you don't get salt marsh, you'll get freshwater wetlands as well. And I just have a few more slides. But if you really want to know what's going on with Patuxent Marsh, I'll go back to that image from 2021, that color infrared. On the left is what the LiDAR tells you, what the actual individual cells of the elevation. And it's completely clear what that marsh is going to look like maybe in 10 or 20 years. You're not going to have any of those fingers left. Those are too low. The water level is going to get too high, and you're just going to have a fringe of marshes around the edge. So the real utility of LiDAR, I think, is predicting which marsh units are going to disappear first. All right, what can you do about it? I keep on telling my science partners that all marshes are doomed. It's hopeless. Just accept it. But there are things that you can do. One thing that I'm actually a partner on a project is this SNEP-funded project to construct runnels which drain these pans. Now, this is putting ditches in marshes, an old technique to control mosquitoes, right? But they used to do these great big, long, wide ditches, very deep. So they're trying to find a less damaging kind of approach, and they came up with runnels. And runnels can be dug with a modified clamshell device like this, where you're only scratching a shallow distance, still mostly within the root zone of a marsh, or you can do them by hand with a small shovel. Again, you're not going down very deep. The goal is just to take these pools of standing water and create a little path for the water to go. And I'm told that sometimes you can even just like pressing down with your foot, you can create a little runnel. So what they did in this study is to build the runnels and take the dredge material, which you could never put in a marsh before, but they got a permit as part of a habitat restoration for salt marsh sparrows to make little mounds throughout the marsh, because salt marsh sparrows need a slightly higher elevation, that to be a particular elevation for their nests, so they don't get, their chicks don't drown. So they used the material that they scooped out to create these runnels and created some salt marsh sparrow nests. And it was the first time the dredge spoils were permitted to be put back on the marsh. And here's an example of one of the sites. So before November 2020 in the runnel, that's what this series of pans look like. And then after the construction of the runnel, on the bottom photograph, you can see the runnel off to the side on the right. I have a little arrow to it. And the vegetation came back. And this is true at a number of sites. Some sites, it wasn't, especially the deeper pools, you don't see this kind of change. But if it's a shallow pan, you see the recovery of the marsh. Another thing that managers are looking at is called thin film deposition of sediments on marshes. This has not been permitted in Massachusetts, but it has been permitted in Rhode Island. And I have a link here to this CMRC website in Rhode Island. It had a lot of partners, a lot of scientists were involved, where they had a clamshell digging up a channel and then putting a slurry of sediments onto the marsh. And again, you can go through the storybook, but you know, it shows you where the marsh was, the sediments were added. The depth of the sediments is one of these images. And then you had to plant grass on those sediments. So it's an expensive process. It's laborious. You're not going to do this in many places. This is like a high priority site that you want to restore. But they're evaluating and it seems to have some success. Not permitted in Massachusetts. And then the final option is to protect land that allows for marsh migration. This is a site in Dartmouth upon Narragansett Bay near Nonquit. You can see the salt marsh, which I've highlighted in yellow, a 2001 image and a 2021 image. All those little island marshes are disappearing. But below the edge of the salt marsh, you see that wet area. It's probably a freshwater wetland. And as sea level rises, we're going to have this new salt marsh that is now a freshwater wetland. It's going to be turning into a salt marsh. So that may be decades from now, but there will be some large areas of marsh migration in certain areas. I can show you places like this in Wareham, Mattapoisett, Marion, Dartmouth, and Westport. You don't see so many places like this, but you can find some small spots in Bourne and in Falmouth.
Just because you mentioned permitting, for the runneling, has there been any runneling that you're aware of that's not associated with mosquito control? Because that's usually been the exemption that's allowed that, because without the mosquito control, you wouldn't be able to permit that within marshes as well.
That is correct. Although we did get the permit to include the spoils on the marsh,
Yep.
which is new. The partner on this project was Mosquito Control Department of Food and Agriculture within the state. And so they were a partner and they did the work. So you're right. Trying to get this done without their participation would be a lot harder. Absolutely. And that's it. I'll stop there.
Do you have any more questions for Joe? And that was quite a run through.
So I gave you a lot of slides. I used up my hour. I assumed I had an hour, so I used up my full hour.
There's a lot of information.
That's great.
I appreciate that.
Yeah.
Good work.
And we'll have this stuff, we'll post.
Okay, so just in between 2019 and 2021 or 2022, have you really noticed differences over that short period of time that since you started it, or what's 2018 to 2021?
Well, what we're doing is using my historical analysis. And right now I'm only focusing on 4 dates, 2001, 2009, 2014, and 2019.
Okay.
So that's the basis of the study right now, is my interpretation of the historical photographs. Within the shorter time frame of them going out in the marsh just in a couple of years, the only rapid changes we're seeing is where we're altering the hydrology, the runoffs.
Yep.
They're seeing some small things in those transects, but you're going to need probably a decade to see some real trends. I mean, I showed you that image of the stickless marching down the marsh. That was over a 5-year period. So you're probably going to see that a similar thing happen in some of their transects. But the edge loss, that's you need generally decades to document the trend.
Thank you.
Yes.
I
Certainly
have a
appreciate
quick
it.
question, sorry, if
ahead.
we have time. It should be quick. Joe, I saw you had one of the potential effects for salt marsh loss, salt grass loss was crab predation, and then you did, there was some crab population. Do you think that it's been green crabs? I know that that's a really big problem, especially in northern New England. I wasn't sure if that's the population that you're seeing that's potentially affecting the salt grass down in your way. What do you think?
On the Cape Cod studies, mostly they're blaming the purple marsh crab, which for some reason has gotten very abundant. I've heard some people talk about the green crab, which is also very abundant and gotten problematic in some marshes. And we're counting them in some of the crab trap studies, but I haven't followed it close enough to definitively say it's them versus the purple marsh crab.
Okay, thanks.
Anybody else? We need to get on with the rest of the meeting. Joe, thank you very much.
Okay.